just a few announcements, just a heads up about things that are due. I sent out an email a few days back, just with some reminders. So hopefully by now you've all watched the video on my lecture pertaining to logarithmic and exponential equations. And as I mentioned, today's the problem session for that. And the homework for what we're going to be covering today, that homework's going to be due Friday. So just keep that in mind. With the quiz due Sunday. So there's a quiz due Sunday, and the next workbook assignment is due this Friday as well. So, which is going to be talked about during the Friday review session by the tutors. And also I mentioned about the deadline to sign up for the final exam. So if you haven't done that already, please make sure you do that before the deadline. So yeah, that's pretty much the announcements, all characterized by what was sent out in the email. So since there's only two of you, I'm happy to take any suggestions for problems you might want me to work first. This is for the logarithmic and exponential equations section. So if there's a specific problem either of you want me to work out, I'm happy to do that one first. Otherwise, I'm just going to arbitrarily work out problems from the that I didn't talk about in the notes. So does anyone have any specific problems for me to work out, or just want me to work problems? And that's fine. If you have any questions later on, you could just let me know. No worries. So all right, cool. Yeah, no problem. So I'll just work out problems that looks like I didn't cover in my lecture. So all right. So I suppose I'll just do problem one to just warm up the idea, kind of the theme of the first half of the problems, because this homework is set up in two themes. The first theme is going from logarithmic to exponential, and the other theme is going from exponential to logarithmic. So we're looking at the first direction, rewriting from logarithms to exponential to help us solve equations. And I'll just do this one just as a warm up. So really the idea simplifies to having some logarithmic expression simplified, so that way we can use that rewriting method. I think in my video I might call it a windmill method or a loop method. It doesn't matter. It's just a method that illustrates how to rewrite a logarithmic expression as an exponential. It tells us that the 3 goes first, followed by the third power is equal to x. So 3 to the third power, pretty sure that's 27. So if this is okay, then hopefully that's just a warm up. But yeah, these are the types of ideas that we will ultimately be simplifying towards. It's definitely helpful to know these conversions moving forward. And so let's see. Let's look at another problem. And I think I did this one already, but I'll just do it here, just again to emphasize. So same idea, that 4 is considered a subscript or the base, more appropriately the base of the logarithm. And you wrap the 4 around the 2 and point it at the 7x, and that tells you exactly to write this as 4. If then the next number is 2 is equal to 7x. 4 squared is 16, which is 7x. X is 16 divided by 7, which doesn't really simplify. So again, this might just be basic stuff for you. I just want to give an introductory idea or warm-up idea as to how these conversions work. So hopefully so far all of this is okay. So we'll go ahead and so I did talk about this problem. In fact, I talked about 8 of the first 13 problems, which hopefully should be helpful. And in my video, I talk about 8 of the 13. So I'll go ahead and skip around a little bit. This one looks a little bit more unique. Yeah, I don't think I've talked about this one, so I'll go ahead and discuss this problem. I'll start off by just rewriting it over here. So the difference between the previous problem, the previous 2 problems we worked on in this one, well, obviously, there's 2 logarithms instead of 1, which is going to change our thought process a little bit. When we have 2 logarithms on separate sides like this, it's good to have them set equal to each other because the logarithms can at some point be canceled out, but they cannot be canceled out right now. The reason why is because we need to rewrite powers as factors, or factors as powers. So you might remember this from some of the previous problems, but generally a logarithm is not considered isolated, fully isolated, until you rewrite all of its factors, which are the numbers in front, as powers. So hopefully you remember this power rule. Same with the 2 being applied to the 4. So this is log base 5 of x to the 1 over 3. All we did was move that number in the front of the logarithm as the exponent. And on the right-hand side, log base 5 of 4 squared, because we moved that 2 as an exponent of 4. This is the power rule of logarithms. And so now each logarithm is isolated. It's by itself, which is fantastic because now we can cancel out the logarithms. So notice log base 5 and log base 5 cancel. So it works out perfectly. But just keep in mind, logarithms are not isolated. I'm going to highlight it. Logarithms are not isolated if there is a number in the front of the logarithm, like that 2. You have to move the 2 somewhere else, which we moved it as a power. So please keep that in mind. And so we have x to the 1/3 is equal to what ends up being 16. And then we can apply, well, remember, x to the 1/3 is the same thing as the 3rd root of x. And how do you get rid of the 3rd root of x? You take the 3rd power. So x is equal to 16 to the 3rd power. That's probably a pretty large number. Just go ahead and knock that out right fast. 16 raised to the 3rd power, 4,096. So these are the types of, this is the type of thought process you need to have. In particular, some way of isolating logarithms in some sense. That's pretty much going to be the theme of all of these logarithm-based problems. And the means for which we isolate the logarithm will be built upon the rules that we've learned in the previous section. The product rule, the quotient rule, and the power rule, which we'll see those ideas moving forward. So hopefully that's okay so far. All right, so I'm going to go ahead and erase this and we can look at another problem. So it looks like I covered this problem in part 3 of example 1. So I'm going to skip it for now. And doesn't seem like I talked about this one. So I'll talk about number 6 as well. Two log base 2 x minus 8 plus log base 2 of 2 is equal to 3. And I like to put parentheses around whatever the logarithm is evaluating. They don't do it in the statement of this problem, but I do. If you put parentheses, it's not going to affect your answer. So that's just a stylistic preference, but it won't affect your answer if you have to type in logarithms and you put parentheses. So really for these types of problems, so we have two logarithms like we had in the previous problem, but they are not on separate sides of the equal sign. And in fact, they are right next to each other with a plus sign. Now, there's really two ways to go about this problem, and I think one way is a lot more simplistic than the other. The first thing that you would like to look for, and really this applies to any sort of problem we've seen before, we can ask ourselves, do any of these logarithms simplify? As in, do we have any logarithmic expressions in this problem that are nothing but numbers? And the answer is yes. This right here, that's all numbers. So I'm curious, can I simplify that expression that I just underlined in red? Can I simplify that to an even nicer number? So let's pull that off to the side. Here's some scratch work off to the side. Log base 2 of 2. So the question is, can we simplify that to a nicer number? Well, what's the calculator-friendly form of this? It's log of 2 divided by log of 2. It's log of what we are evaluating divided by log of the base. So this is something I've talked about in my previous video. I've probably mentioned it in the video for this section as well. And the only reason, so I call this the calculator-friendly version because you can put all of this in your calculator. So log of 2 divided by log of 2 is just 1. So really off to the side, we just found that this whole expression is just 1. So if we can do that in the beginning, we simplify the problem big time. This would be 2 log base 2 of x minus 8 plus 1 is equal to 3. So notice how much nicer this looks now. And we could just subtract 1 on both sides, because they are like terms. So that's after we subtract 1 on both sides. So now we have a single logarithm, which means it goes back to the very first example we looked at. But we need to isolate the logarithm. We need to isolate the logarithm, which means the logarithm is not by itself yet. It looks like it, but that 2 is in the way. So we need to find a way to get rid of that 2 in the very front of the logarithm. We can either divide both sides by 2, which would be easier, or we can raise the 2 as a power. You'll get the same answer. One way is going to be a lot more simplistic than the other. I'm going to divide both sides by 2. Which then gives us log base 2 of x minus 8 is equal to 1. And now we have isolated the logarithm, which means we can use this windmill or this loop method, which tells us exactly that 2 to the first power is equal to x minus 8. Or once you work it out, x is 10. And so that would conclude problem 6 here. So yeah, there's these various characteristics that are good to look out for, because if you can identify them, such as if you have a logarithm with all numbers, you could simplify that really quickly. It's going to simplify your problem big time. But that is only if you have a logarithm of all numbers, no variables at all. Because that's something we can, with all numbers, we can put that in the calculator and hope that we get a more simplified number. So does anyone have any questions about any of the problems we've done so far, or should I just go ahead and keep going? If not, I'll just go ahead and keep working more problems. Okay. So I do talk about this problem. In fact, I talk about this exact problem on part 4. I mean, it's number for number. So I'm going to skip 7. I'm going to talk about number 8 here. Now, all right, we have 2 logarithms. They are on separate sides of the equal sign. And so the first question really is, well, the first thing I like to look for is, do we have any logarithms that are just numbers? Just numbers, no variables in it. And the answer is no. Because if we did, we can try to simplify them. They don't always simplify very nicely, but there's no logarithm with all numbers, so that idea is out the window. So we can't simplify any of the logarithms independently like we did in the last problem. So now it's a question of, can we set the logarithms equal to each other? Which means we would have to isolate both logarithms. Well, there's a problem with that. We will not be able to isolate both of these logarithms because that 1 is in the way, that 1 plus. If we move the 1 to the other side, then it's just going to interfere with the other logarithm. So that 1 is ruining everything. So instead, we need to utilize a way of taking the 2 logarithms and combining them together as 1 logarithm. And that way we can isolate the single logarithm instead of the impossible task of isolating the 2 logarithms. So what I'm going to do is not move the 1 over. I'm going to move this logarithm over by subtracting it. So that's log of 7x plus 4 minus log of x minus 7 is equal to 1. And the reason I did that is because we know how to combine 2 logarithms together as 1 when they are being subtracted, provided they are isolated individually. Now, both of these logarithms are isolated. There's no numbers in front. There's no interference. We could just subtract these directly. And so what I'm going to use, remember, when it's a difference of logarithms, we use the quotient rule. So I'm going to put the quotient rule here. I put QR, quotient rule. So this allows us to combine two logarithms as a single log. Remember the quotient rule, well, there's a quotient somewhere. The 7x plus 4 goes on top, and the x minus 7 goes on the bottom. That's equal to 1. And now we have combined two logs together to get a single log, which is now isolated. It's now by itself. There's no number in front of the log. There's no plus 1 to it or anything. Now that we have the logarithm isolated, we can now use the loop method or the windmill method, whatever you want to call it. We can convert this to an exponential function. Now you start with the base, but there's no base, which is kind of interesting. There's no base in this problem. The logarithm is just, it seems kind of bare. But when there is no base, you assume that the base is 10. So base 10, that's the assumption here. You assume that the base is 10 when there's no base. And that's just like the base 10 counting system that we use. It's sort of implied. So you assume that the base is 10. And what this tells us is that 10 to the first power, because we count the 1 next, and all of that is equal to, well, really the whole entire fraction. 7x plus 4 divided by x minus 7. And from here, we're going to really simplify. What it ends up simplifying as in essence, a linear equation. We can multiply both sides by x minus 7. So we just cross multiplied. We can distribute the 10 right fast. So that's 10x minus 70 is equal to 7x plus 4. We combine some like terms. 3x is equal to 74. I don't think that simplifies nicely. So x is 74 divided by 3. Let's check and see if that answer is correct. 74 divided by 3. So this is the general process, the general thought process you need to have. Can you simplify things in the beginning? The answer was we couldn't simplify any of the logarithms that had just numbers because we didn't have any of those. The question remained, can we set the logarithms equal to each other? The answer is no, because there was that 1 in the way. So we had to bring the logarithms together and combine them as a single logarithm. And then we converted to an exponential function and went from there. So does anyone have any questions about this process? If not, I suppose let's just look at another problem. I think I'll go ahead and do this problem as well. I'll go ahead and do problem 9 as well. So I'll go ahead and start off just rewriting it. And so again, my general thought process, my most general thought process is, at first, are there any logs that I can simplify? Is there any logarithm that is just numbers? And if so, can I cross my fingers and hope that this would simplify to a number? And the answer is no. We don't have any logarithms that are just straight numbers. It's all symbols. Every logarithm we have has an x involved. So the next question is, well, with the two logarithms, can we set them equal to each other? And the answer is no, because that 3 is in the way. That 3 will prevent any of the logarithms from being simultaneously isolated on both sides of the equal sign. And so really what we want to do is in the same sort of flow as the previous problem, which is we have two logarithms that are actually already next to each other with a plus sign in the way, which is good because we have a formula for that. This is the product rule of logarithms. So what we're going to apply, and notice there's no numbers in front of the logarithms, which means that we don't have to rewrite anything. We're going to apply the product rule immediately. Just have two plain logarithms that are being added to each other. And that means we construct a single logarithm where we multiply the contents of each logarithm, just like that. It goes from two logarithms to a singular logarithm whose evaluation is the product of the inputs of the individual logarithms. And from there, we have now isolated a logarithm on one side of the equation, which means we can now use that method that I've been mentioning many, many times over. What this tells us is that 5 to the third power is equal to x plus 32 times x plus 12. And unfortunately, this is going to be a quadratic. So it's going to be a little bit painstaking. So 125, and we can go ahead and FOIL, first outer, inner, last. Squared plus 12x plus 32x plus 32 times 12, which is 384. Well, let's go ahead and keep combining like terms to ultimately get that 0 is equal to x squared plus 44x, it looks like. 34, 44, and then 384 minus 125. It's 259. Interesting. 259. So actually, 259, so if we try to factor this using guess and check, we would have plus signs. It turns out that 37 and 7 gives us the result. I just took 259 and started dividing by random numbers. I found that 259 divided by 7 is 37. Guess what 37 plus 7 is? So it works out perfectly. So then we get that x is equal to negative 37 and negative 7. So hopefully everyone's okay up to this point so far. Now, the problem is, if you try to type both of these answers in, it's going to tell you not so fast. It's going to give you an error. And it gives you a fairly vague answer, but it does give a little bit of insight in some portion of this response. In fact, the last sentence. Be sure to reject any values that produce a logarithm of a negative number or zero. So you might also think, well, both of these are negative numbers. Wouldn't it be no solution then? Because you toss the negative numbers. Again, not so fast. That's not right either. So you might think, okay, well, what is this even asking for? Did we do the problem right? The answer, we did. Hopefully I did everything right. But one of these answers works and the other one doesn't. And the reasoning why, so with logarithms, we do have to check our answers. So we do have to check our answers with logarithms. Normally the rule of thumb is that the larger answer will be the correct one. The larger answer is -7, which does work. And so the reasoning why is because if we think about log base 5 of x plus 32, for example, well, one of the answers we got was that x was -37. Which gives us log base 5 of -5, which does not exist. So notice that 37 or -37, it's not the fact that the solution itself is negative. It's the fact that plugging that solution back in to the original equation will give a domain restriction. So -37 doesn't work. But if we were to plug in, say, -7 plus 32, so what is that? That's 25, I think. We can take the logarithm of a positive number. We can't take the logarithm of a negative number. So that's why this is okay. It's because the plus 32 is large enough to turn the -7 into a positive input for the logarithm. And that's why we only accept -7. And I wanted to emphasize that. In some problems, there might be, both answers might work. Some problems, the largest answer might work. And so you have to be a little bit careful about which one you choose. But the overall generalization here is you can't assume that a solution being negative or positive will instantly imply its validation or its validity towards being the solution, the final solution of the problem. It may be negative as a solution, but still a valid solution because of how it's applied to the original problem when we check our answers. So that might be just a bunch of jargon, but basically be aware of checking your answers is kind of the theme here. And so from there, if nobody has any questions, I'll just keep going. So doesn't look like it, so I will go ahead and continue. I think I did this one already, so let me check. So I did a problem very similar to this in part 5, so I'm going to skip that one. I did this problem. As you can see, it's almost the exact same problem in part 6. This one is part 8, actually. And I'm guessing this one is part 7, which it is. So I suppose everything I've covered, as well as the lecture video, covers at least the first 13 problems from the homework. So, and the first 13 problems being conversions from logarithms to exponentials. So does anyone have any questions before I move on to the other half of the homework? If not, no worries. I could just keep working problems. So with the next problems, as I mentioned before, the goal is to utilize the conversion from exponential to logarithmic. So exponential to logarithmic to help us solve problems. And this is generally when we have variables in the exponent, which without logarithms are, without logarithms, these variables are hard to get out of the exponent. So let's go ahead and look at some of these problems. So I did 14 exactly in the notes. Maybe I'll skip ahead to, well, I'll do this one just as a warm up. I also didn't talk about it, so it works out perfectly. So let's say you're trying to solve this problem. 5 raised to the x is equal to 2. And so you ask yourself, can I get the 5 as a base of 2 or the 2 as a base of 5 so I can cancel out the bases? This was a process you did in the very first section for the Unit 4 material. And the answer is you cannot rewrite 5 as a base of 2. The 5 and the 2 are just, they do not have a common base that you can get to, at least not easily. So this is when we have to use logarithms. Logarithms help us rewrite exponentials as logarithms. And in essence, what this does is it takes variables in the exponent and makes them more grounded in a somewhat spatial aspect, so a more literal aspect than you might think. And really, there's two ways, and I believe I talked about this in my lecture video. There's two ways you can do these problems. And one way is using logarithms, and the other way is using natural logarithms. Now, really, both ways, either way is going to be fine. And in fact, I'll use the log method over here and the natural log method, and you can just pick your favorite. It really doesn't matter. Now, it may seem like the log method is easier because the log method says, well, you know how to rewrite this as a logarithm. It's the formula. It's that formula of, I've written it in several ways. A to the x is equal to y is the same thing as log base A of y is equal to x. So it's just the formula. So log base 5 of 2 is equal to x. So notice in one step, we were able to isolate the x by simply using the conversion formula. That's all I did. I just used the conversion formula. And if you worked it backwards, you would verify that this does correspond to the exponential equation that you had in the beginning. So yeah, x is equal to log base 5 of 2. And notice that the base of the exponent is the base of the logarithm. And so you could put that as an answer. Or you can use natural logs, which it may seem a little bit more cumbersome now. It is helpful in other problems later on. But the natural log way requires you to apply a natural log to both sides. Notice the only change so far is the stylistic application of the natural log symbol. And then that allows you to apply the power rule. X natural log of 5 is equal to natural log of 2. And then from here, x is equal to natural log of 2 divided by natural log of 5, because you have to get x by itself. So you divide both sides by natural log of 5. And so this answer is also, this answer would also be accepted. So really, this will accept either answer. Now, the reason why the natural log version is better to use than the logarithm version is really in reference to this next part here, when it says, what is the answer rounded to 3 decimal places? And so the difference between these two is that over here on the natural log side, that is already calculator ready. You can type in ln of 2. In fact, I'll go ahead and do that right now. Type in ln of 2, close parentheses, divided by ln of 5. And it says 3 decimal places, so 0.431, it looks like. The logarithm aspect of things, the logarithm here is not in a calculator-friendly form at its current stage. You cannot put subscripts in the calculator. So you would have to rewrite it. You would have to rewrite it as log of 2 divided by log of 5. And then you would put that in the calculator. So no matter what, and log, and just to verify, this and this are the same for reasons I'm not going to get into. They're a little bit outside of the scope of this class. But those are the same. You could plug either one into the calculator and get the same exact answer. But that's kind of the give and take of each way, of each method of doing the problem. And there are certain benefits to using one method over the other in maybe a specific case, which we will talk about in these next upcoming problems. But for this problem, here's 2 different ways to solve this problem, one using logs and one using natural logs. Does anyone have any questions about this? If not, I'll just go ahead and keep going. So I did problem 16 for part 2. So I'll go ahead and skip that one. And I also talked about 17 for part 3. And I'll talk about number 18 here, since it seems like I think number 19 is, yeah, number 19 is that one. So I'll talk about 18 here. And I like to write out the problem. 5 to the 1 minus 6x is equal to 6 raised to the x. Now, this is another situation where you have the exponent stuck, or the variable stuck in the exponent, which is normally in consideration of a logarithm, because obviously 5 and 6, you cannot get the same base. So that's when I think of logarithm, to get a variable or variables out of the exponents. Now, this goes back to that idea of, should we use logarithms or natural logarithms? And honestly, I think that using natural logarithms is an easier way of doing this. I don't think I worked it out using logarithms, but really the thought process you should have is that there's not one variable and one exponent that you're trying to get out. There's 2 variables and 2 different exponents you're trying to get out. The logarithm only applies, or is only helpful for one situation of this, in my opinion. And the natural logarithm will help with numerous variables. So again, because there are 2 different variables, or 2 variables and 2 different exponential expressions, that's why I want to use the natural logarithm. And remember, the first step of applying the natural logarithm And I'll just set up this first. The first step is simply just writing natural log. So notice the first step is just the application of the symbol. I haven't changed anything else so far. And now, the beauty of using natural log is that I can take exponents to the front. Take exponents to the front. That's why the natural log is so helpful. It allows me to move numerous exponents to the front of the corresponding natural log. The only thing you have to be careful of is the whole exponent has to stay together, as in, notice I am putting parentheses around 1 minus 6x, natural log of 5. I'm putting parentheses around 1 minus 6x because that whole exponent needs to stay clumped together. If you don't put the parentheses, you're going to lose that association of the exponent. But over here, the x is just by itself, so there's no need to put parentheses. So from here, so again, it's important to keep that parenthesis around the whole exponent if there's more than one term, because you need to remind yourself that that whole exponent is one entity. It's got to stay together. And so from here, this now motivates for us to distribute the ln of 5. And what we get, so 1 times ln of 5, so exactly what we get is ln of 5 minus 6x ln of 5 is equal to x times ln of 6. So notice all I did, the 1 has an ln of 5 and the 6x has an ln of 5. And I multiplied those terms accordingly. So now this is kind of a difficult aspect because we have two x's that we're trying to solve for, and we're dealing with these lousy natural logarithms. So what we have to do here, the most simplistic process here, we need to get these x terms together. So we're adding 6x ln of 5 on both sides. And there's a reason why I'm doing this. And this will make more sense after I write everything out. The reason why I moved all the x terms together is so now I can factor out the common x. By putting all the terms that have an x in together, we can now say that since they all have an x together, we can factor out the x. So notice this is a reverse distribution. This is a reverse distribution of the x. And now notice we had 2 x's and now we have only 1, which is perfect. Now that final x is what we need to solve for. And more so, that x is multiplying what ends up being just a collection of numbers, which we can now divide. So what our final answer would be is natural log of 5, natural log of 5 divided by natural log of 6 plus 6 natural log of 5. I know it's not the prettiest answer, but this is kind of logarithms for you. This is natural log of 5 divided by natural log of 6 plus 6 natural log, plus 6 natural log of 5. And now it wants us to round the answer to 3 decimal places. And this is, first I'll see if anyone has any questions about what we've gotten to so far. So does anyone have any questions about this process so far? If not, I'll go ahead and keep going. So when we plug this into the calculator, the good news is it's already calculator ready. Anytime you use the natural log process, your final answer is automatically going to be calculator friendly. But, and I emphasize this heavily, the way you type this in the calculator may not be correct. You have to, in the calculator, put the denominator in an extra set of parentheses. You have to do this. If you don't do this, the calculator doesn't understand that the denominator is enclosed together. It doesn't understand. It doesn't know that. How do you tell it that the denominator is associated together? You have to put parentheses. So those red parentheses that I have will I'm trying to figure out the right word here, associate the denominator together and not split it up. And so now I'm going to type that in directly. I'm typing in ln of 5, close parenthesis, divided by, and I'm going to open up parenthesis, and then put ln of 6, close parenthesis, plus 6, ln of 5. That extra parenthesis around the denominator, it not only helps, it will distinguish between the right and the wrong answer. 1, 4, 1. So if you did not get this, first let me make sure that my answer is correct. 0.141. If you did not get this answer, then that means you typed it in the calculator incorrectly. And you really need to make sure that you could type it in the calculator correctly, because that would be very unfortunate to get the right answer in part A, but then the wrong decimal, which might cost you a few points, say, on the final. So, does anyone have any questions before we move on? Okay, we'll go ahead and erase this and we'll move on to some other problems. So I think the next problem I worked out already. Yeah, so 19 is part 4 from the lecture video, so I'll skip that one. Number 20 is part 5 from example 2 in my notes and in the video, so I'll skip that one. Actually, yeah, so that's correct. I think we're going to do 21. Let me check right fast. All right, so this one's number 6. So, okay, I'll work out 21 then. Since this one has a few things going on simultaneously, which I didn't explicitly address in my lecture video. So I'll go ahead and do this problem. Two to the 2x plus 2 to the x plus 1 minus 48 is equal to 0. Now these problems, admittedly, get a little tricky because there is a U substitution feel to this. There's a quadratic feel to this. But the substitution is not ready to be implemented quite yet. And we did a problem dealing with what happens when you have an x plus 1 here. In fact, I've talked about this situation in the lecture video for part 6, what you do when there's an x plus 1, and I'm going to re-explain that idea right here. What you do is realize that this is the same thing as 2 to the x times 2 to the first power. So this is a property of exponents. So in other words, we are rewriting this expression as 2 times 2 to the x. So notice what the plus 1 did is it gave us another base of 2, which we just moved to the front of the exponent. And now we have a form that could be applied to u substitution, which I'll write over here. So the u is actually going to be 2 raised to the x. So this is a little bit difficult of a problem, I think. But the u substitution is 2 raised to the x, which is perfect because the second power of that is 2 raised to the 2x. So really, this right here works out to be u squared perfectly. This part right here is u. And so now we have that u squared plus 2u, because that extra base of 2 is still out in the front, minus 48 is equal to 0. So I don't think the factoring is much of an issue. There's a plus and a minus. So what is that? That's 6 and 8. Is that right? Yeah, 6 and an 8. So an 8 goes here and a 6 goes there. So we get that u is negative 8 and positive 6. But remember, u's are not good enough. We need x's. We need an x as a final answer. So that's when we need to remember the rule. U is equal to 2 raised to the x, which gives us 2 situations. Negative 8 was one of the u's, and 6 was one of the u's. Now, hopefully, you remember that an exponent, so we can actually cross this one out immediately, because exponential functions or exponential expressions do not output a negative. They work just like the square root functions. If you forget this idea, then you would find out very quickly that you would end up taking the logarithm of a negative number, which is not possible. So instead, we turn our attention to the rightmost expression. And this way, you don't have to check your answers. So this is what we get. Again, you could type this in the natural log fashion. So you could have also written this as a natural log. Natural log of 6 is equal to natural log of 2 to the x, which means you could pull the x out to the front. And so x would be natural log of 6 divided by natural log of 2. So that answer would also be acceptable. In fact, that answer will honestly be helpful for the next part. Because the next part wants us to round to 3 decimal places. This form right here is not in a calculator-friendly version, but this form is. The natural log of 6 divided by natural log of 2, which is what I'm going to go ahead and plug into the calculator. Natural log of 6 divided by natural log of 2. And so I get 2.585. So that's one of the substitution-based problems in this homework. I think I do the other two in my lecture video. Does anyone have any questions about this before I move on? Okay, cool. So we've got to go ahead and erase that and see what else I haven't covered. Okay, so let's move on. So this is a substitution problem. This also resembles part 6 in my lecture. So I'm going to go ahead and skip that one. Let's look at other ones. I think I'm going to do 23. Let me check the other ones. Yeah, because 24 is part 7 in my notes. So let's see, 23. And I also talk about 25. That's part 8, as you can see. What's 26? Oh, and I talk about 26 at the bottom here in example 3. So I think I'm going to do 23, and that'll be every problem from the homework. Okay, cool. So I'll talk about 23 here. So this is 4 raised to the x minus 12 times 2 to the x is equal to negative 36. And so this is actually another substitution-based problem, even though it may not look like it. It's definitely a tricky one as well. So if anything, we can go ahead and add 36 on both sides. Oops. So plus 36 is equal to 0. So we just added 36 on both sides. And so now we need to figure out what the u substitution is. Well, naturally, it's the middle variable expression. Naturally, the u is always the middle variable expression, but does that generalize here? So if we were to, so this is scratch work off to the side to just convince ourselves. 2x squared is equal to 2 raised to the 2 times x, which is 2 squared to the x, which is 4 raised to the x. So that's more so convincing yourself of that. You don't have to do this. But 4 raised to the x is indeed 2 raised to the 2x. So that means that the u substitution is u squared minus 12u plus 36 is equal to 0, which we could factor pretty easily. We'd have 2 minus signs, and it looks like it's 6 and 6, which means we have, less answers to worry about. So we get u as 6. And from here, well, we need to recall what the rule was. The rule says that u is equal to 2 to the x. And there's only one answer, so there's only one thing that we have to plug in. That 6 is equal to 2 raised to the x, which you can solve either using logarithms or natural logs. So you would get either x is log base 2 of 6, or that x is natural log of 6 over natural log of 2, depending on which way you do it. The reason why the natural log way is helpful is because it immediately sets you up for putting in the calculator. In fact, this was the same answer for the last problem. So 0.585. So it just turns out we got the same answer as the previous problem. Natural log of 6 divided by natural log of 2. And so that encompasses every homework question, either from my lecture video or from this homework review session. I've covered all 26 problems. So if you have any questions, I'll stick around. We still have 9 minutes, but other than that, you're free to go.